Let's first consider all the forces that are acting on the ladder. We have the normal force that is available from the contact between the ladder and the wall, which we will denote by F normal 1. Since the wall is smooth, there's no friction. There's no friction force acting on the top of the ladder. On the bottom end, we have the contact force between the pavement and the ladder, Fn2, which is strictly upward. And then in order to prevent the ladder from sliding, there has to be a static force of friction, F sub s, pointing to the right. At the center of the ladder, we're going to have W1, which is the weight of the ladder, and then 1/3 up the ladder is going to be W2, which is the weight of the person that's climbing the ladder. And if you note from your trig, since the ladder is 5 meters long and we have a 53.1 degree angle, you can use sines and cosines to find that this is a 3, 4, 5 right triangle for this problem. Now if we consider some of the forces in the F direction on this ladder, we're going to see that we have the force of friction is pointing to the right, and the normal force from the wall, F sub n1, is pointing to the left, so we're going to make that a negative. And since the ladder is in equilibrium, it's not sliding, falling, or accelerating, the sum is going to be 0. And then if we do the same for the sum of the forces in the y direction, we're going to have the normal force excuse me, from the pavement going up. We're going to have the mass of the person, which is 800 newtons, going down, and we're going to have the mass of the ladder, which is 180 newtons, going down. There are no other forces in the y direction, so that has to be 0. And now we have to consider one more thing, which is the torque. And if we consider the torque about a certain pivot point, and let's take the pivot point to be the bottom of the ladder, so this is going to be our pivot point. Then we can say that the sum of the torques around the pivot point, let's call that point P, is going to lead us to, notice that there's a length of 4 meters from the bottom to F sub n1. So that force F sub n1 is going to contribute a counterclockwise torque that is 4 meters away from the pivot point in the vertical direction. We have M, W1 and W2 are pointing downward, so if they acted, it seems like the ladder will go in a clockwise, and that is a negative torque, so we have 180 newtons. Now, if the ladder is halfway up, then this is going to be 2.5, which means that half of the 3 is going to be a 4. Half of the 3 will be 1.5, sorry, I don't know what I say, 4. This would be 1.5 meters is the distance that's vertical from here to here. From the pivot point to this point would be 1.5 meters. And then we have the 800, which is the weight of the person, and its distance we want is from here to here. It's 1/3 up, so it'd be 1/3 of 3, which is 1 meter. And then notice if we take F sub n2, then since it's at the pivot point, there is no distance there, which is the same for the force of friction, and this will contribute all the torques in this system, and that has to come out to 0 as well. Since we only have the unknown is F sub n1, we can solve this for F sub n1, and we notice that F sub n1 then is going to equal about 268 newtons. Once we have F sub n1, we can find out that F sub s then is going to be from this equation, the top one, F of s then is also going to be 268 newtons because they're equal to each other, right? They cancel each other out. So this would be part A. Let's move on to part B, which asks us for the coefficient of friction to prevent the sliding. And if you remember that the force of friction, F sub s, is the mu sub s times the normal force associated with it. In this case it would be F sub n2. So this means that mu sub s for an equilibrium position which is not moving is F sub s over F sub n2 and in order for us to find F sub n2, we can use the equation for the sum of the forces in the y. We notice that it's 980, so this becomes 268 newtons over 980 newtons, which is 0.27. Keep in mind that whenever you're finding coefficients of frictions, whether it's kinetic or static, you want to be between 0 and 1. And now if we want to look at the forces at the base of the ladder, we can say the force sub base of the ladder is going to be F sub s in the I hat direction plus F sub n2 in the j hat direction, which means this is 268 newtons I hat plus 980 newtons j hat. So the magnitude of this force then would be the square root of 268 newtons squared plus 980 newtons squared, which is about 1020 newtons. And the angle for this F sub b is going to be the tangent inverse of 980 over 268. Notice that they're both positive, so this gives us about 75 degrees, and we have found the magnitude and direction of the contact force at the base of the ladder. And this ends our example.